Hi Year 10. Right now we're looking at differentiation still, and we're up to 8J from the Cambridge textbook, Rates of Change. I guess this topic is pretty much looking at a more of a practical style of our differentiation, and a lot of people find this one quite a little bit harder than what we've done so far. So don't panic if it's a little bit different and harder, because it is. Okay, so let's have a look through the notes in here. What we have been looking at so far is our dy dx's, and we've also looked at, when we've looked at parts and the product rule and the quotient rule, we've looked at du and dv, so du dx, dv dx. We really haven't discussed what it means in the real world or physically. We've just differentiated things with respect to x. So we've basically just been finding our dy dx. But I guess we've had a little look at a du dx and a dv dx, but everything's been in relation to x, and looking at functions that are called y. However, that's not always going to be the case. Not all functions are written in terms of x and y, and here's a few examples of what we could see. dq dz, one that we will look at in a minute, is a dp dz, which p would be population and t would be time, so we might look at population growth over time. Bottom one might be a force with respect to x, and differentiating between those terms. So it doesn't always have to be a y and an x, and it definitely won't be when we're looking in the real world. So here's something that's more physics based. However, in physics you will not be differentiating, but it relates back to physical calculus in the physical world, which we'll have a look at in year 12. So if x was distance, and we go up and have a look at x and time, so distance and time together, we think about what distance over time is. Distance over time is speed. So if we differentiated x with respect to t, like this, dx dt, we'd actually get our speed. If we were then looking at the quantities of speed and time, and we think about what speed over time is acceleration. So if we differentiated speed with respect to time, we'd actually get acceleration. But if we think of it as then differentiating our dx dt, or our speed with respect to time, would also be the same as differentiating again our dx dt. So we get a second derivative of dx dt, and that's also acceleration. So that's something we'll have a little bit of more of a look at next year. These three parts below here are really important for us for now: increasing, decreasing, and stationary. So when we consider the gradient at each point of the curve, which is the first derivative, which is the gradient of the tangent, these three results here are possible. We're going to suppose that y is equal to f of x, and it's at some point a, x equal to a. So we've got f of a in there. So the a is generally just a number on the curve. We're very familiar with this middle one here. This middle one here, and we've been looking at it in terms of when dy dx is equal to 0, or we can think of it as f dash of a equals 0, or f dash of x is 0 at a. It's a stationary point. So we know that that is a gradient of 0. So a dy dx equal to 0, there is no slope, the gradient is flat, and that tells us there is a turning point or a stationary point in a curve, and that's something we're going to need to continue working with. We haven't had a lot of a look at these other two sides here. If our function, or our first derivative, sorry, f slash of a is bigger than 0, so if we think of what that means back in terms of the gradient, if our dy dx, or our gradient of the tangent, is greater than 0 at a point A, then we have a positive gradient, which would be going this way, and we will say that our curve is increasing. It's going in this direction. Likewise, if we think of the opposite of that down this end here, if our dy dx is less than 0 at some point x is a, our gradient of our tangent is negative. It's looking like it's going this way. Think back to just general slopes in our earlier years of school. We would say then our curve is decreasing. We're going down this way. So we're going to be having a look at these three parts of our derivatives in the following questions. I think they're really important because sometimes we're going to be given a formula and we can straight out differentiate and work out what's happening in terms of our dy dx, and sometimes we're not given a formula at all and we need to think about these three things. So what the curve might look like, and relate that back to increasing, decreasing, and stationary. That's just what this bit here says. This important information can tell us a lot about the system. The stationary point is especially important as it tells us when the original function is not changing. So that's when our gradient of the tangent is flat and it's equal to 0. In some problems, we may know roughly what the graph of some of the quantities is against time or some other variable that's on the denominator, but not the equation. In these instances, we need to use tangents and relate them back to the idea of increasing stationary and decreasing to see what is happening. And that's what's happening in this first question here. And we're going to work through this one now. So in this first question, we are given a diagram. We've got a T for time at the bottom and a T for temperature at the side, but we're not given an equation. Now let's read what we know from the question. And it says, the graph shows the temperature T, that's this axis of the graph, of a patient at time T hours after her admission to hospital at midnight. So we're thinking along these terms. A patient goes into hospital at midnight and we start monitoring the temperature, and the temperature's up here, okay? 3 hours later, the temperature's increasing up to a maximum point, and then it starts decreasing. So after 6 hours, it's still decreasing and decreasing. When we get up to 9 hours, it starts to flatten out, and it looks like it's going to stabilize and continue along. And I'd probably call this line here an asymptote. So it looks like it's continuing on, and then it stabilizes down there. That is the only information we have about that graph, and we need to answer some questions based on that now. So let's look at part A. The question is saying, when did her temperature reach its maximum? So this one's fairly straightforward. She's coming to hospital here at midnight, and this is her temperature. We don't know what the value is, but we know at that point it's increased up until we've got to 3 hours here. So that's our maximum there. So the maximum happens at T equals 3, which is 3 o'clock in the morning, or 3 a.m. because she's coming at midnight and it's 3 hours later. So that's our first one. It's a fairly simple one. Let's have a look at part B. When was her temperature increasing most rapidly? And when was it decreasing most rapidly? And when was it stationary? So I'm going to take you over to another little graph that I've done. I think will help us a lot with this one. I'm going to jump over to this question over here. Where are we? Here we go. So what I've looked at here is the graph, and what I've actually done is I've popped tangents in there at various points. So, and that's what our dy dx is looking at. It's looking at the tangent of the curve at various points along there. So I've popped in this black one here at t equals 0, and look how steep that tangent is, or how big that one is there. If I've moved up a little bit, I've got the red one. Okay, it's at a point a little bit further up, so it's up there. The first one was down here. It's a little bit flatter, okay, and I've picked a third point up here, and that's up about up there, and it's the dy dx, or the gradient of the tangent, is flatter again until we get up to 3, and 3 is where it's very flat. It's a gradient of 0. So let's think about how that's going to help us answer that question. So the question said, for B, when was her temperature increasing most rapidly? So I've just jumped back to your notes that we just looked at in terms of increasing, stationary, and decreasing. So our curve is increasing when it is, our f dash of A is greater than 0, and the bigger the f dash of A, or the bigger the gradient of the curve, so the larger that value is for dy dx, is going to relate to when it's increasing most rapidly. So if we jump back into my little diagram that I've done over here for you, the graph is increasing most rapidly right down here when she's admitted into hospital. Okay, t equals 0, and that would have been midnight. It is a steeper tangent than at the other points. Okay, so that's when it's increasing most rapidly. It also said when was it decreasing and when was it stationary. So we've done increasing. It's stationary. Well, that was easy. We've already looked at stationary. Stationary occurred at t equals 3 hours, so 3 o'clock in the morning. That's when we had our gradient equal to 0. It was the turning point. And when was it decreasing most rapidly? So it's decreasing most rapidly, and I haven't drawn those points on the graph here, but if you were to go through and draw another heap of tangents along this curve, got another one there, put another one there, another one there, Another one there. What you're seeing is as I go down that curve, the tangents are getting steeper until I get to 6. And when I get down to 6 o'clock in the morning, I've got the steepest tangent going in the other direction. Okay, so we think about what that said back in our notes, and I'll jump back across to those topic notes for us. What that said was, when we're going in the other direction, and we have a derivative that's less than 0, which is what's happening in our graph, the curve is decreasing. And we're wanting to find when it is decreasing most rapidly, and it is decreasing most rapidly when we have the steepest tangent in that direction, which is going to occur for us at t equals 6 or 6 o'clock in the morning. So they would be our 3 answers for that. Let's pop that over here. So it's increasing most rapidly at time equals 0. It's decreasing most rapidly at time equals 6 or 6 in the morning, and it's stationary at time equals 3. Let's have a bit of a look at C. What happened to her temperature eventually? We had a little bit of a talk about that right at the start. So her temperature, once she gets down to 9, is starting to smooth out. It's starting to stabilise, and that little dotted line there would be an asymptote. So that temperature would continue to move along that line like that, and that would be her base temperature, which will be about 37.5 degrees or something like that. So that's stabilising, and that's all we need to write for that one. Our second last question, we need to graph the rate dt, and sketch that. Okay, so I'll finish off the notes for that question in the next video, and we'll graph the dt graph, and then we'll have a look at when that's increasing and when that's decreasing.